Okay, so we are ready to start. The problems on today's session, as I was just telling you guys, will be mostly about the homeomorphisms and properties of that, as well as the T0, the T1, the Hausdorff, the regular, some of those concepts from chapter 5 that we started learning about. And I like to kind of combine them. So here's a problem that kind of puts homeomorphisms together with this T0 condition. Maybe we could refresh our memory over here what T0 means. So x tau is T0. Can you guys remind me of the definition?
For every x not equal to y, there exists a neighborhood that's around one of them that not equal to the other.
Okay, so for all distinct points of the space, there exists, let me just call it an open set, U in tau, with, well actually it doesn't, with one of the elements in U and the other not in U. Okay, so that's what it means. Okay. So if we have a T0 space and it's homeomorphic to another space, we want to show right here that that other space is T0. Okay? I think you guys are going to be doing the same thing for Hausdorff in the next homework assignment. So this is kind of a very similar problem. So to show that y, so instead of starting with the assumptions, I think you should start with the thing you're trying to prove right here. So we're going to take two different points of y. So let's call them, y1 not equal to y2 in capital Y. So grab two distinct points of y. And our job is to come up with a neighborhood of one of those points that doesn't contain the other. Okay. So we have to create this neighborhood, right? Well, let's think about this. We know that anytime we have two different points of x, we can create a neighborhood in capital X that has one of the points in it but not the other, right? That's the assumption here. So if we had two different points of x that we could work with, we could apply the T0 property to that. But I'm starting with 2 points of y. So what do you think I should do next?
So fs equal y, right? You're using fs equal y.
F of x?
Equal y.
Okay, so you're talking about an f.
So we're going to use the pre-image.
So a pre-image, you're talking about a function, right? So there has to be a function. Because we have a homeomorphism, there exists a function. So I think the next thing, if we're going to take advantage of what you guys are saying, we should write down the homeomorphism, okay? So let's do that here. So we are given, and we don't know the formula for the homeomorphism, but we are given a homeomorphism F that goes from x tau to y tau prime. So how can I now use that to come up with two distinct points of x? Sometimes I like to draw these pictures. So you have x here, y is here. Our function goes like that. We're starting off over here with these 2 points. Okay? But what we know is that x is T0. So how can I start working with x?
So you're going to use the f inverse, right?
Okay, I'm going to take the f inverse, and there is an inverse because this is a homeomorphism.
Yes.
I'm going to go back here. I'm going to find a pre-image for y1, and we can call it x1. And then similarly, there's a pre-image over here, which is x2. They have to be different because you can't have one dot on the left side going out to 2 points on the right side.
Because
So,
it's 1 to 1 and onto.
Exactly. So it's not because of 1 to 1 and onto. It's just because of the definition of a function. So because of a definition of a function, these 2 points have to be different since they go to 2 different points. Exactly. Okay, so we can then let x1 equal the preimage of y1 and x2 equal the preimage of y2. And note that x1 does not equal x2. Okay? So two different points in the domain correspond to those points y1 and y2. Okay, now what should I do next?
So you're gonna to use the assumption T0 in the S tau, yeah.
Exactly. The original space is T0. So if I have two different points, then we already know that there exists a neighborhood of one of them that does not contain the other. And without loss of generality, we can assume that that neighborhood contains x1, but not x2. Okay, so since, very good. So since x tau is T0, without loss of generality, there exists a u in tau with x1 an element of u and x2 not an element of u. Okay, very good. So we can find an open set here. Let me just draw a picture. Maybe this is my u right here. Okay, so u contains x1 but not x2. My goal is to come up with an open set in y that contains one of these points but not the other. Is anybody seeing where I'm going to get that open set from?
The F inverse of U.
So if you look here, I can't take f inverse of u because u is on the left side. I can take
The
f of u, but I
Oh,
can't
yeah.
take
Yeah.
f inverse of u.
Or the
So-
pre-image.
Yeah,
Right.
F inverse of inverse, right?
Okay, the pre-image of the
Okay.
inverse
Oh, okay.
function.
Uh.
Right, or, right, so we could just, yeah, I think that's probably just as good of a way to say it. So, so then, if we take the pre-image of f inverse of u, right? So the f inverse function goes this way, and the pre-image of it is actually, guys, what this is equal to is just f of u, right? It is just f of u itself. And that is still open because f inverse is continuous. Remember that the homeomorphism preserves open sets. So this is actually in tau prime. So we do know that this is open. And in addition to that, let's see, does this set do what we want it to do? Well, so the f of u we're hoping is something like this, right? So is y1 inside of it? y1, well, y1 is, what is y1? y1 is f of x1, and x1 is in u, so this is an element of f of u. Okay, and y1, or sorry, y2, which is equal to f of x2. Now, we want y2 to be outside of this open set, right? So in other words, what we are wanting to say here is that it is not in f of u, right? Now, my question to you is, how do I know that it is not in f of u? By the way, is this a true fact? If x2 is not in u, then does that mean that f of x2 is not in f of u? Is this true, generally? This actually is not necessarily true. Just because x2 is outside of u doesn't mean that the function might push it into a place where it was actually the image of some other element that was in u. But the only way that this could ever happen that this was not true would be if the function was not one-to-one. See, guys, look, if you look at the picture here, so f of x2 is equal to y2. If y2 was in f of u, right, then that would mean something from u would have to map to y2 also, and now you have a failure of the one-to-one property. Okay, so I just want to say this is not clear. This is since f is one-to-one. It's not always true that just because x2 is outside of u, that f of x2 is outside of f of u. Okay, does that make sense? The picture kind of helps you to see what's going on. Okay, so we're pretty much done. We found an open set in Y that contains one of our elements but not the other. Okay, so Y comma tau prime is T0. That's the end of the proof. Look okay? Okay, very good. Okay, let's go on to another problem. If everybody, are there any questions here? So you're going to want to do, you're going to be doing this again for T2 or T1 or something. This is a great model to help you with writing up that proof. Okay. So these are some good problems that I've got for you today. Make sure that you go back later and try them again on your own. Get out your YouTube and just pause it and see what you can do on your own, and then you can watch the replay if you want. Okay, so let's do this one, number 2. Let's let x be the open interval 0 to 1. And let's let u be an element of tau if and only if u is equal to either the empty set, or u is equal to the whole x, or u is equal to the open interval from 0 to 1 minus 1 over n, where n is a natural number. Still looking for a better marker here. Try this one for a little while. Okay. So this is basically telling me what my open sets are going to be. The open sets in this topological space are going to be the empty set, the whole space. You have to have those. And then all intervals of this form right here. Okay. So, so in other words, you know, tau would equal the empty set, the whole space. When n is equal to 2, you get the interval from 0 to 1/2. When n is equal to 3, you get the interval from 0 to 2/3. When n is 4, you get the interval from 0 to 3/4, and so on, like that. So it's all of those sets, and have to convince yourself that this really is a topology. So it has the two sets you always have to have, and then it has to be closed under finite intersections. The thing with these sets is that they are actually nested. One within the next, within the next, within the next. So if I take any two of these sets and I intersect them, I'm just going to get the smaller of the two, which is still part of my space. And similarly, if I take any union, of these sets, you're just going to get the biggest one, right, that you have. So this is definitely a topology. So then the question that I want to ask is x comma tau T0, T1, Hausdorff, and or regular. Remember that regular is just a shorthand for it, T1 and T3. So, by the way, don't forget about the quiz next Wednesday. You have to make sure you learn all these definitions. for Wednesday. So I've got the T0 definition still on the board over here, but we have to kind of think about all of the definitions. So it might be okay. Do you guys remember the relationships between these concepts? Like which ones imply which ones? So T0 implies T1?
No, T1 implies T0.
Right, T1 implies T0. Hausdorff
Implies
implies
T1.
T1, and regular implies Hausdorff, right? So, for example, if it's not T0, then it can't be any of these, right? Or the other way around, if it is regular, then it has to be all of these, right? So, I would suggest if you get a question like this that you start on one end or the other. Don't just start with the middle, because then you're not going to know which way to go from there. So maybe since we have the definition of T0 on the board already, we can think about whether this space would be T0 or not. So what do you guys think? Would it be true that for any two different numbers between 0 and 1, that you could find one of these sets that had one of the elements in that set and the other one outside of that set? 0 and 1. So if we take any two numbers here, right? Will we always be able to find an open set that contains one of them but not the other? I'll give you an example. This is what you have to do if you don't know how to answer the question. Try an example. If I take 0.1 and 0.9, those 2 points, right? Well, I claim that I can separate those 2 points because, for example, the interval from 0 to 1/2, right, contains this point but not this point. So for those 2 points, we can do it. The question is, for all distinct points, if I take any two different points, will I always be able to find one of these guys that I can separate the 2 points with?
That's not true.
You don't think so?
It's not for all of them.
Not for all of them. Okay,
Yeah.
so
for example, if
so-
you look at the point 1/4.
okay, so let x equal 1/4 and y 1/3. Okay, so those points are both over here in this side of it. So 1/4 is about right there. 1/3 is maybe there. Right, something like that. So the question is, do we have one of these intervals that contains one of those points but not the other?
No.
The answer is that every single one of these sets that I'm underlining
both, okay.
has both of those points in it. And the other set that I didn't underline has neither of those points. Okay? So there does not exist. So this is a pretty easy question. Like this could be like a really good little test question to just test the definition here. There is no U in tau such that U contains exactly one of the 2 points. So x is not T0. It's not going to be T0 in that case. So far so good? Make sense? Okay, great. Pretty easy. Okay, I'm going to go ahead. And if it's not T0, then it's also not T1. It's not Hausdorff. It's not regular. Remember that T1 just means that singletons are closed. Well, you can definitely see that singletons are not closed here. If you take a single point, right, its complement is not going to be one of these intervals. So singletons are not closed, so it's not T1, definitely. Be sure that you're keeping track of the examples of spaces that are T0 but not T1, T1 but not T2, and the T2 but not regular I have to do on Wednesday. That's a slightly more complicated example, but anyway, the counter examples going the other way, you want to kind of remember those. Okay. Okay, let's go on to another example here. It's going to be number 3. Okay, so I'm going to give you a definition here. So we say that x comma tau is disconnected if there exist u and v not empty, but u and v are in tau. So there's two non-empty open sets with u intersect v empty and u union v equal to the whole x. Okay. So a space is disconnected if we can express it as a union of two disjoint open sets that themselves are not empty. I can't just cheat and make one of them the empty set and the other one the whole space. I have to be a little more careful than that. Okay, so otherwise x tau is connected. Okay, so this is the definition. And I'm going to ask you about 3 questions about this. Okay. This is the kind of thing I like to do. I like to give you, like even on a test I could do this, I give you a definition you never saw before, but that is based on the material, and ask you to think about that definition with some things that are a little bit more familiar. So the first question here, there's going to be 3 parts to this. The first question is going to be, is n, this is the natural numbers n, connected using the what's called the cofinite topology. I've been using this a lot. I just don't call it the cofinite topology that often. This just means that the closed sets are either the finite sets, the finite subsets, and the whole natural numbers. So we've looked at this example many times. Every time we have a new concept or a new definition, I like to apply it to this example to see what we can say about it. So what I'm asking here is, can I express the natural numbers as a union of two open sets whose intersection is empty and the two sets are not empty? I'll let you guys think about that for a second. Can I write, so remember, the open sets are the ones that have a finite complement. A finite complement. So can I have two of those sets that have a union, it's the whole natural numbers, finite complement. Vin, do you have any idea?
No.
So an open set would be something that is only missing. I'll give you an example. So one example of an open set would be this open set right here. That's open because the complement is finite, and so the 1, 2, 3, 4 is closed. So the complement of that is open. Okay. So if that was my U, okay, it's non-empty, it's open. Now I have to come up with V. V has to also be open.
And
Is it okay for this to be V?
No,
No.
because this is gonna be closed, and we should have the union of U and V to make the whole natural numbers. So there's no way to do that.
Yeah, there's no way to do this, guys. There's no way to do this because if both of these sets are open, then they both have to have a finite complement. But look at what is the complement of U. If U intersect V is empty and U union V is the whole space, then the complement of U is exactly V, right? Like in other words, X minus U is V, and X minus V is U. They are each other's complement. So you're saying on the one hand that U and V have to be open. That means their complements have to be finite. But if both of these sets are finite, then their union can't be all of the natural numbers, right? So the answer here is that it is impossible to come up with the U and the V here. So is it connected? The actual answer is yes. It is connected because it's not disconnected. Okay? So let's just write that down, just a very short explanation. So notice that N is not disconnected. N is not disconnected since any U in tau has a finite complement which must be V. Okay, but then V is not in tau because its complement is U, which would be infinite. Okay, so I don't know how to say it much better than that. That's basically the idea, right? Does it make sense?
Mm-hmm.
See what I'm saying? The way you have to remember when you're thinking about this space is the open sets are huge. They only exclude a few finitely many points. So if the open sets are huge, it's going to be very hard for them to have an empty intersection. Right? They're going to have to have some things in common. Right? Okay, so thus N is connected. Thus N is connected. Okay, great. So we have that. Now let's do a part B for this one. Okay, so for part B, I would like to show that connectedness is preserved by homeomorphism. So if you have two spaces that are homeomorphic and one of them is connected, then so is the other one. Or if one of them is disconnected, then so is the other one. Okay, so that's kind of a nice thing to do. So prove that if f that goes from x tau to y tau prime is a homeomorphism, then if x is connected, so is y. So if x is connected, then so is y. Okay. Well, assuming that x is connected means that x is not disconnected. In other words, that would mean, so the assumption that x is connected is really telling us that x fails to be disconnected. In other words, there do not exist U and V non-empty open sets whose intersection is empty and whose union is all of x. We're saying there does not exist all of that stuff. Well, that's very hard to work with in a proof. The assumption is that there does not exist a whole bunch of stuff, right? So I would recommend that we do not do this proof by starting here.